Okay, good morning, everyone. Today you're going to start the study of transformers. Or I should say we will study transformers. We'll devote one lecture to transformers, even though a transformer is not an actuator nor a power electronics component. The reason you're going to study transformers today is that most electrical machines will behave internally as a transformer. So a good understanding of how transformers work is essential later on when you're going to address induction machines, for example. In the induction machine, we have a configuration that resembles that of a transformer. So we're going to study here. Later on, we will apply this to electric machines. In this lecture, we're going to review the principles of transformers and model and analyze a non-ideal and a ideal transformer. And again, this will set the foundations for some electric machines that we will study later. The first thing we need to know to understand how transformers work is, again, Faraday's law and Lenz's law. We saw that from lecture 2, that if we have a current creates a steady magnetic field, but a magnetic field does not create a static current. In Faraday's law, we have this example here with two coils. The first one is connected to a battery. And when you close the switch, a current flows through this winding. This current creates a magnetic field. And this magnetic field, if the current is constant, is also constant. In Faraday's experiment, he connected this second coil with a multimeter. And the second coil, when exposed to the first constant magnetic field, had a voltage of 0 volts at the output here. However, Faraday noticed that as he was opening or closing the circuit, the switch, he noticed that that voltage would change. An induced voltage would be measured there anytime the switch opened or closed. And therefore, he concluded that that voltage is proportional to the change of the magnetic field in the primary coil. And this is what we call the electromotive force, the EMF. A changing magnetic field creates an induced EMF, an induced voltage in a wire that is exposed, in a conductor that is exposed to that same varying magnetic field. So now the idea of a transformer is quite simple. Instead of having a DC voltage, why not having an AC voltage? Close the circuit and have the same multimeter there. Now this magnetic field is changing over time, is an alternating magnetic field. Its derivative is no longer 0, and therefore the voltage that we should read in the second multimeter is always non-zero. And this is the principle of a transformer. Lenz's law is the extension of Faraday's law, and Lenz's law cannot quantify exactly how much is produced, but it can specify the direction of that induced EMF, and that direction comes with this sign. And this sign is, again, very important because it has a fundamental meaning behind it. It states that this induced EMF will create a current that in turn creates a magnetic field. And this created magnetic field must oppose further changes in the originating magnetic field. That's what this negative sign means. Otherwise, we would have created free energy. If the current created a force that would attract this magnet, for example, then the magnet would accelerate, the speed would increase, and the EMF would therefore in turn increase, which brings us to an infinite loop. So that negative sign has a lot of meaning here. First, it's the balance of forces that act on this magnet, and the second is the direction of the current is given by that sign. So in this second configuration here, instead of one wire, we have many wires in a loop, and you're approaching this magnet. We see that we close the loop and put a multimeter there. From Faraday's law, we can now state that this induced EMF is proportional to the number of turns of that wire times the derivative of the magnetic field over time. And Lenz's law adds that a negative sign, which specifies now that a current generated through this induced EMF must oppose the magnetic field created by the originating magnetic field. In this case here, if the magnet is going down, let's assume that its magnetic field is H. You see that it creates a current I in the conductor. I, if you use the right-hand rule, if you follow the current direction, we see that the resulting magnetic field is upwards. And this is the resulting magnetic field from the current I, which opposes the magnetic field of that magnet. So the magnet will experience a force moving it against its velocity. So here we have then Lenz's law and Faraday's law. The amount of current generated in this loop is very simple. We take the induced EMF and divided that by the resistance of that wire. And that is the magnitude of the current. So this is just a review of what we saw in the last lecture. Now in a transformer, we'll combine that idea that we saw in the beginning with two coils that share the same magnetic field. But for maximum efficiency, we are going to use something to direct the magnetic field from one coil to another. And typically we use a material of very high permeability, so that the required force to create an EMF, the required electromotive force to create an EMF, is very small. In this example here, from this configuration, we have an iron or a high permeability core, typically iron or something with a relative permeability that is very high. We have a first winding, let's call that the input, or we can call that the primary winding as well. It's simply a coil that is wrapped around the core. And we have a secondary winding with a different number of turns than the primary winding, which is again built around the same core. This is, of course, a simplified configuration because you have the two coils that are separated. But if you look at an actual transformer, they will overlap. They are always wound around the same core and they overlap. So now we have two coils. We have a shared magnetic core of a high permeability. The reason, again, is that way we can concentrate the magnetic field in the core. The EMF required to establish a flux is a lot lower than the EMF required to establish a flux in the open air, right, compared to the very first configuration. Now we have these two windings here. Each of them, the primary and the secondary winding, create its own magnetic flux. Or let's put it this way, if there is a magnetic flux in the core, then each wire is subjected to its own electromotive force. Let's look at the first one. If you neglect the resistance of the winding, then you can say that the first voltage across or the relation between the voltage and the magnetic flux in the first winding is N1, the number of turns of the first coil, times the derivative of the magnetic flux. And you can say the same for the secondary coil. It shares the same magnetic flux, and the equation is the same. Now the induced force, the induced voltage in the secondary coil is N2, the number of turns of the secondary coil, times the derivative of the magnetic flux. This is an ideal transformer. So what are the assumptions here? The first assumption is that there is no resistance. These wires have no resistance, which allows us to write that the induced EMF at the output here is equal to the induced EMF at the coil itself. This does not hold if we consider that the wire has a resistance. But if there is no resistance, then the EMF and the applied voltage are exactly the same. The second assumption is that the magnetic flux is confined to this magnetic core entirely. There is no leakage magnetic flux, meaning that there is no flux going through air. It's all confined in the magnetic core. The third assumption for an ideal transformer is that the permeability of this magnetic core tends to infinity. The permeability of the magnetic core tends to infinity. In other words, the required EMF to establish a magnetic flux is, any guesses? If the permeability is infinity, what is the required EMF to establish a magnetic flux? 0. And the required EMF would be 0 because there is no permeability. There is no reluctance. The permeability is infinite. It is the same as saying the required voltage to establish a current in a circuit is 0. All right, so now if you take these two equations and combine them, we can isolate for d phi dt in one of them. So let's take this one, d phi dt equals to v2 over n2, and then replace that in the first equation. So d phi dt is simplified, and we end up with this expression, the relation between the input and the output voltage, or the voltage in the primary and the secondary winding. V1 over V2 equals to N1 over N2. And this is equal to A, where A is the turn ratio, the number of turns in the primary divided by the number of turns in the secondary. If A is greater than 1, then this will step the voltage down. The input voltage will be greater than the output voltage. If A is smaller than 1, then the voltage in the output goes up compared to the input. It's easy to remember that the side with the highest number of turns is the side with the highest voltage. And this equation then relates now the input voltage and the output voltage. Three assumptions again. Windings have no resistance, no inductance, no flux leakage, so all flux is confined in a core. And third, the permeability of the core is infinite, no reluctance. Okay, so this is a review of physics. I believe you saw this in your first year. Now related voltages, let's relate currents. If we think about the generated flux from each coil and we think about Lenz's law, the net EMF in the core must be 0. The EMF from one coil, let's say this coil here, creates, let's say, a magnetic flux phi1. The EMF in the secondary winding, because of Lenz's law, will need to create a magnetic flux because of this current that goes in the opposite direction as phi1. Otherwise, again, we run into an infinite loop, which means that the sum of all EMF must be 0. They must oppose each other. Right? This is very important because that gives us the direction of the output current. Let's look at this diagram once again. If the magnetic flux goes that way, going like that, so goes downwards, so the current will have to be turning. In this case, the induced current on the other side must be creating a magnetic flux that points up, which means that it must be turning, what is this, counterclockwise, right? So the direction of or Lenz's law gives the direction of the output current. So if I ask you in a hypothetical midterm question, what is VC? If it's positive or negative, how do you answer that? Well, it depends on the direction of this magnetic flux created by I1, because we know that I2 must create its own magnetic flux that opposes phi. So it needs to go that way. And based on that, you know in which direction the current is flowing. So again, another implication of Lenz's law. To maintain this balance, then the sum of all EMFs must be 0. And here we have the EMF from both coils, their number of turns times their current. Subtraction is 0. The sum is 0. They have opposite signs. And from this, we can now establish a relation between the currents. I1, if you rearrange the same expression, I1 over I2 equals to N2 over I1, or 1 over A, where again, A is the number of number of turns, the turn ratio, N1 divided by N2. Another implication of having a practical transformer is that by saying that we have, an ideal transformer, is that the input and the output voltages or powers, the input and output power, must be conserved. So we can write that V1 I1 equals to V2 I2, where V is the root mean square of the sinusoidal voltage in the input. Right? This is very important because when you rate transformer, we are always talking about root mean square, not the maximum or the peak voltage, always the root mean square. That's something to keep in mind. Okay, so if you take the root mean square of the input voltage, this holds. The input power equals to the output power, and this makes sense because there is no resistance, there is nothing dissipating power in a ideal transformer. Now let's connect a load to that transformer. We have a load Z here, and if you connect a load to the output of that transformer, then current I2 flows, as we just saw, which means that a current I1 will also flow in the primary winding. The power dissipated in Z will be taken from the power source. The power dissipated in Z will be taken to the power source. So if you are dissipating 10 watts here, these 10 watts are coming from the power input. This simple scenario, we have a input voltage, we have the transformer with a turn ratio of A, and you have the output impedance Z. This makes the analysis a bit complicated. But knowing that if we connect this impedance in the output, that impedance takes power from the input sees that impedance in the secondary winding as having an equivalent impedance in the primary winding. We can refer the secondary winding impedance to the primary and then calculate, say, I1. And then from there, can calculate I2. So for the analysis that will follow later, this impedance transfer is very important. So the question that you are trying to answer now is, if we connect Z here, a impedance Z, from the power source perspective, what is the equivalent impedance, given that in this process of power transferring, we have this turn ratio of A? We can define the impedance on either side as V divided by I. So from the secondary side and the primary side, we have them here. Now we can take Z1 and replace V1 with V2 times A. Remember, from V1 over V2 equals to A. We can take I1 and replace I1 with I2 over A. That comes from I2 over I1 equals to A. Just replacing the voltages from that we see in the primary and the current writing that with respect to the secondary winding. This is now easy to manipulate. We see A divided by 1 over A, that is A squared, and we have V2 over V1, so this is equal to A squared times Z. So the equivalent impedance as seen by the primary is A squared times Z. Okay, that's the equivalent impedance seen by the primary. We connect Z in the secondary, but from the primary's perspective, that impedance becomes A squared times Z. Okay. So the secondary impedance will have an effect on the overall impedance of the system. It makes perfect sense. And we need to do this transfer, otherwise we would be delivering free energy to the secondary winding without affecting the impedance of the primary winding. That doesn't make sense. If you have to go the other way around, if you take an impedance from the primary winding and you want to reflect that in the secondary winding, then we would do the opposite. Z2 would be Z1 over A squared. All right, primary impedance in the secondary winding. And the original equation here is the secondary impedance in the primary winding, as seen by the primary winding. I don't think there's much new here from physics. Are there any questions there? No? Oh, all right. This is indeed relatively simple. Nothing really new here. Now let's look at a practical transformer. In a practical transformer, now we need to account for all losses and all imperfections in a transformer. If you look at an ideal transformer or a practical transformer, now we have a magnetic core that does not have an infinite reluctance. It needs some EMF in order to magnetize itself. What else? We have magnetic fluxes that are not going through the core. They are looping around the coils like this. We call them leakage fluxes. And we have an implication, another implication of Faraday's law, the eddy currents that are developing in the core. So the core has this alternating magnetic field, and as we saw before, it's a closed loop conductor. There will be a current actually flowing in the core itself, and that current dissipates energy in the form of Joule losses. That's the eddy current from lecture 2. So we now need to compensate for all these elements. So let's just start here by analyzing what we call a no load current. If you attach nothing to the output of the transformer and simply connect an input voltage here with nothing in the output, unlike the ideal transformer, there will be a current flowing in. This current, we'll call that I0, is the no load current, and this is responsible for two things. The first one is to magnetize the core, is to create this magnetic field that overcomes the reluctance of the magnetic core, establishes this first magnetic flux in the core. Because again, we have a finite permeability. The second part of I0 is dissipated in the form of heat, in the form of eddy currents in the magnetic core. And what is the relation between these two? Well, the one that magnetizes the magnetic core, I phi, is in phase with the magnetic flux. Right? The magnetic flux, we know the relation between that and the current is proportional to the current, so they are in phase. The voltage input to the core and IR are also in phase, so I phi is in phase with the magnetic flux, and IR, that one that is dissipated in the form of heat, is in phase with the input voltage. Now, what is the relation between them? Are they in phase as well, or are they out of phase? Let's assume that our magnetic flux has a sinusoidal waveform as given here. Magnetic flux is the maximum magnetic flux in the core times a sinusoidal waveform, sine of omega t. Omega is the frequency in radians per second. What is the induced EMF? What is the electromotive force? It's negative n times d phi dt. So now if you take the derivative of this, let's neglect that negative sign for now, as we are interested in the magnitude. That becomes, omega comes out, sine becomes cosine, and we have n times the magnetic flux. So now notice that the relation here is from sine to cosine, which means that IR, the current that is dissipated in the form of heat, and I phi, the no load current that is responsible for magnetizing the core, are 90 degrees out of phase. So these are 90 degrees out of phase. And this is very important because I0, the no load current, is not simply I1 plus I phi. Why not? Because they are 90 degrees out of phase. So let's plot the phasor here. We have I phi in phase with phi, and we have I0 in phase of V with V, and we have a 90-degree angle between them because of the sine and cosine. What is I0? I0 is the vector sum of them. That is, I0 squared is equal to I1 squared plus IR squared. So I0 is the square root of I1 squared plus IR squared. I phi, sorry, this is I phi. Right? And this is very important because now we cannot simply say that I1 equals to, or I0 equals to I5 plus IR, because they are 90 degrees out of phase. We now need to add them back in a vector form. Any questions here? No? All right. Okay, so let's continue then. If you have questions, you need to ask me with your microphone because I'm not keeping track of the chat. Very well. So this is the first thing we need to account for. A no load current, again, responsible for two things: magnetizing the core, providing the initial magnetization of the core, and some of that will be dissipated in the form of Joule losses because of eddy currents. Something very important to remember is that these two components are 90 degrees out of phase, so it needs to add them in a vector format, not necessarily, not just I0 equals to I5 plus IR. That doesn't hold. The next thing we need to consider in a non-ideal transformer is now the windings will have a inductance. And this inductance is an additional impedance in the circuit. These impedances will also be used to represent the leakage magnetic flux, or those magnetic fluxes that are not looping in the core. They are looping in the air around the core. Right? So the flux going through the primary and the secondary winding are not necessarily the same anymore. To do that, we need to define what an inductance is. And we can relate the inductance with another quantity that is very common in electrical circuits, in magnetic circuits, which is the magnetic flux linkage. Magnetic flux linkage. I have no good interpretation, physical interpretation for the magnetic flux linkage. The closest I can get is to say that the magnetic flux linkage is the magnetic flux times the number of turns in a coil, or how many magnetic flux lines are there with respect to the number of turns in the coil. That's the best interpretation, very poor interpretation, but that's the best one I found for the flux linkage. The magnetic flux times the number of turns. From Lenz's law, the inductance is a property of a conductor which opposes any change in the current through the conductor. It makes sense. In a winding, we pass a current through the conductor that creates a magnetic field. That magnetic field doesn't like changes in the magnetic field, because the changing in the magnetic field creates its own current in the inductor. And that current opposes the originating magnetic field, opposes changing in the first magnetic field. That's the whole definition of an inductor. So we can define the inductance as the quantity that opposes changes in the magnetic field. And an easy relation to keep in mind is magnetic flux linkage divided by the current. This proportionality constant is the inductance, or how easy it is to establish a magnetic flux in the core. We see here that the lower the current required to establish gamma, or lambda, is that lambda? Lambda. The higher the inductance. Makes sense. From the definition of a magnetic flux linkage, we have N times phi. Phi, if you remember from the last lecture, is the magnetic flux density times the cross-section through which it passes. B is related to the strength of the magnetic field through the permeability, mu h. And h can be taken from the integral of h dl equals to ni, also from the last lecture. So this gives hl equals to ni, h equals to ni over L. Now we can replace everything here. You can follow this derivation in more detail later. We can replace H here, and you can replace B there. And this gives then, and then you replace the whole thing in N sorry, not in N, we replace the whole thing in phi right here. So here we have phi. This whole thing now becomes B. And here we have H, B as a function of H, and as a function of the current in the core. So this derivation will simplify. You can follow this later. It's relatively simple. It's just basically combining the equations that we had in the last lecture. And the final result is given here. N squared divided by L times mu times A. And you recognize this term here. This is the reluctance of the magnetic core. That's the reluctance of the magnetic core. And the inductance now depends on the number of turns of wire squared divided by the reluctance. Let's look at that equation. It makes perfect sense. The more turns we have, the more magnetic flux we create. So the harder it is to oppose changes in that magnetic flux. So the inductance will increase with the number of turns. That makes sense. The inductance decreases with the reluctance, which also makes sense. The lower the reluctance, the harder it is to establish a magnetic flux. So the lower the inductance. The higher or the lower the reluctance, it's the easier it is to establish a magnetic flux, and the harder it gets to oppose that magnetic flux. So the inductance will be higher in systems with low permeability. That makes sense. With low reluctance, high permeability. And this is the inductance now that we created by adding coils to a magnetic core. There is no way around that. It will turn into a impedance. And that impedance is because of this inductance. And you can now use that to model these imperfections, this flux leakage that we mentioned before. So here is the equivalent circuit for a transformer. It looks a bit intimidating at first, but let's see what each of these elements represent. The first one here is the winding resistance. It's simply the resistance of the wire that we are using to create the coil. The second one here is a inductance, or let's call that a reactance, X1. And this reactance is proportional to L, the inductance of the coil that we just discussed. And this is supposed to model flux leakages. Now the flux that does not loop in the core, that loops outside of the core. Then you have these two elements in parallel. We see here our magnetizing current, the no load current, which is split into two. The first one goes through the core that has a resistance R and is dissipated there in the form of Joule losses. And the second component of I0 goes through the core, but is now responsible for magnetizing the core, and that's I phi. So this is all the primary winding. And you see now that our relation between the input voltage and the EMF are no longer the same because you now have all these imperfections in the way. So E1 will be lower than V1 because of the voltages drop across this parallel and series circuit. Now let's look at the secondary winding. The secondary winding, we don't need to account for the core losses because that's already taken care in this parallel branch in the middle of the primary winding. For the secondary winding, we just need to account for the same resistance of the winding and the flux leakage in the secondary winding. If the transformer is loaded, then you can say that a current I1 will start to flow in the primary winding if you add an impedance to the secondary. And you can now say that the current that comes from the power source is much greater than I0, the magnetizing current or the no load current. And this entire branch here can be neglected. only when the transformer is loaded. So if that whole thing can be neglected, then our transformer model will simplify to this. The whole parallel branch is neglected. And now, based on the impedance transfer that we saw before, we can take the impedance from the secondary winding and move everything to the primary winding. Like this. We can add, I think this is flipped. This should be X2, and this should be R2. We can refer this reactance to the primary winding and add that to L1. And you can refer this resistance to the primary winding and add that to R1. In the same way that this impedance can be referred to the primary winding by using the formulas we saw before. What is the equivalent circuit? The equivalent circuit then simplifies to this with a resistance, a equivalent resistance, a reactance, a equivalent reactance, and the impedance of the secondary moved to the primary, or the load impedance in the primary. Let's see for the resistance. For the resistance, we have R1 plus R2 times A squared. That's the impedance transfer that we saw before. Times A squared, because you're referring the secondary impedance to the primary. So that must pass through the number of turns squared. We can do the same for the inductance or reactance if we know the frequency. We have L1. We can take L2 from here times A squared and add that to L1. So here is the equivalent resistance, the equivalent reactance as seen by the primary. And finally, the load impedance is also referred to the primary by simply multiplying the impedance itself by A squared. And we now have an equivalent circuit here. From this equivalent circuit, we can find I1, can find all the voltage drops across the circuit. Any questions so far? No? No questions are either a very good sign or either a very bad sign. One of those. I hope it's the former. But we can also do this analysis in the other way if you want. We can refer all the primary winding impedances to the secondary. The only difference now is that you're going to multiply that by 1 over A squared. Right? This is 1 over A, so the whole thing is 1 over A squared. And R1 is referred to its respective counterpart in the secondary and added, but before that we need to multiply them by A squared. And then you have a primary impedance referred to the secondary winding as follows. Okay, and either way, we have an equivalent circuit that we can now use to find more, to get more information about what is going on inside the transformer, such as the currents. Another thing to keep in mind regarding transformers is the rating. When you buy a transformer, it will come with this information. The power in kilovolt amps, and the input voltage and the output voltage. So this is V at the at the high end, and this will be the voltage at the low end. So what is the turn ratio here? Turn ratio will be V1 over V2, or VH divided by VL. 1100 divided by 110, that is 10. That's the turn ratio. Right, so we have the power, the rated power. We know the input voltage and we know the output voltage of this transformer. We can now find the rated current in the input, in the output. the input current will be the power divided by the voltage, that is 10,000 divided by V in the primary, that is 1100. And this gives, how much is that? 9.09 amps. The output current, you guessed, is the power divided by the output voltage. And this is 110, which gives 90.9 amps. You see the voltage went down from the primary to the secondary, but the current went up by a factor of 10. The voltage went down by a factor of 10. The current went up by a factor of 10. So the balance of power in the input and output is maintained, assuming that this is an ideal transformer again. Okay, any questions at this point before we do an exercise?
I have a question about this. For I2, could we have used the relationship of I1 over I2 equals A, or sorry, 1 over A?
Yeah, and this is exactly what happened. You see, this would be 1 over A. A is, times A, right? The input divided times A is the output current. That's a factor of 10.
Okay.
Yeah, it's the same. If you multiply now this and 10K and that and 10K, we get exactly the same, right? And sorry, I mixed things up. If you multiply this by the input voltage and this by the output voltage, we get exactly 10K. Right? The power is balanced in the system.
Okay.
But it's the same. You can calculate that as well through the current, the turn ratio. Any other questions? Why are there no questions? Is it too easy or too complicated? Well,
so
no.
I have one more question.
Yeah.
So just to clarify, between the ideal transformer and the practical transformer. So in the ideal transformer, we determined, or we identified the relationship A being the number of windings of the input or the number of windings of output. That relationship A, it still exists even though we're looking at practical, even in a practical transformer, that relationship A still exists, right?
Of course.
It doesn't.
Yes, in this non-ideal transformer, then we still have N1 and N2.
Okay.
Yeah. And that's how we transfer the impedance from one side to another, right? It's through A, through that ratio.
Okay, I guess, oh, so that's why in the transformer rating problem that we just did, we don't mind whether if we're trying to assume it's real or if it's ideal or if it's practical. We just know that A is not applicable, or
exactly. The assumption we are making the assumption that it is an ideal transformer because you see that the power is balanced in the output and the input and output, right? But in practice, if we have a non-ideal transformer, this is not true because some power is lost in that process. That's the only difference.
Okay, so some power, when we were looking at practical transformers, some power will be dissipated initially in the flux leakage, right? In the
flux
R1
leakage and core losses. The transformer will heat up because of eddy currents, and some energy is lost there.
Okay.
All right, folks. Any other questions? So if there are no other questions, let's do exercise number 4. In this exercise, we have a 10 kilovolt amp. Was there any question? No? A 10 kilovolt amp transformer, 2200 and 220 volts. So this already gives us the turn ratio. What is the turn ratio here? V1 over V2. And operates at 60 hertz. we are performing two tests. The first test is a no-load test. The terminals of the high voltage side are open. So we're going to apply a voltage in the secondary side and leave the primary side open. And the second test, we are going to short circuit the secondary winding and then apply a voltage in the primary winding. In these two tests, we measured the following: the applied voltage, the input current, and the dissipated power in the transformer. Here are the values. The question is, determine the parameters for the approximate equivalent circuits referred to the low side and high voltage side of the transformer. Okay, is the question clear itself? So we have a transformer. We are going to do two tests. The first test, let's just focus on the first test. We're going to apply a voltage in the secondary winding and leave the primary winding open. And when you do that, we are applying 200 volts. We are measuring an input current of 2.5 amps, and we are dissipating 100 watts. Question: where is this current going? If the terminals are open on the other side, where is there an input current? Where is that going?
It's loading the transformer.
It's loading the transformer. In other words, it's magnetizing the core of the transformer, and part of the current, the power of that current is dissipated in, or the totality of the power input is dissipated in core losses in the form of joule losses. That's where that 100 watts comes from. So let's see if, based on this, we can identify the parameters of the system. So here we have the circuit that we would use. So we have here the primary winding, the secondary winding. It shows as the primary, but it doesn't matter. We are just reversing the transformer and applying an input in the secondary winding. It doesn't really matter. We are applying a voltage here, and you're leaving the terminals open. You see that there's nothing connected in the terminals, and despite that, we still have this current here of 2.5 amps. And what is the current voltage we are applying? 220 volts. And we are dissipating in this configuration 100 watts. If there is nothing connected in the output now of this terminal, then we can neglect the other part of the transformer, which in this case would be the primary winding. And this is the equivalent circuit. We have the input voltage right there. That's this part here. We have to magnetize the core right there. We need to compensate for joule losses. And this is now the part that would connect to the primary winding. But there is no current flowing that way because the terminals in the other part of the transformer are open, which means that the current going this way is 0. Right? There is nothing connected here. There's nothing on the other side of the transformer drawing that current or that power, which means that this part here can be both. Sorry, that's a bit off. That and this resistance can both be neglected, can both be set to 0. The question that we are trying to answer now is, what is the value of this R0? What is the value of that L or the reactance X0? And what is this magnetizing current, and what is the current dissipated in joule losses? This would be easy to do, knowing that it takes 100 watts in the input. All this power is dissipated in R0. It's all dissipated in the core, in the form of joule losses. So what is that power? The power would be I squared times R. This is the only element that dissipates energy in the system. And I is V over R. So if you combine these two equations, we have P equals to V squared over R. We have V and we have P. So R is V squared divided by P. V squared is 220 volts. And divided by squared, divided by the power. $100, and this is 484 ohms. This is this resistance R0. Now that we have the resistance R0, we can find IR. We can find the current through that resistance because this whole part of the circuit is in parallel with 220 volts. So they both have the same voltage. What is IR? What is the value of IR? Simple electrical circuit question. Isn't that VR divided by R itself? 220 divided by R, which gives 0.45 amps. So the current going down here, oops, there is 0.45. What is I0? I0 is given because it's the same as this input current I, it's 2.5 volts amps. Remember that there's nothing flowing that way. This part of the circuit is neglected because there's no current going that way. So I0 and I1, the input current and the no load current in this case, are exactly the same. So through that, we can now calculate the current that flows through here. And how do we find that? How do we find I phi?
It's just I0 minus IR.
Is it? Good that you said that. Is this true? Is I phi I0 minus IR?
Oh no, never mind. It's you gotta do the squared thing.
Exactly, you gotta do the square thing, and it's good to make these mistakes now than later. So this is a squared, square, and squared, right? Because they are 90 degrees out of phase. It's very common, a very common mistake, and it's good that we are now aware of that and are not going to do these during a midterm. That would be a waste of a few marks there. So based on the fact that IR and I phi are 90 degrees out of phase, we can write that I0 squared equals to IR squared plus I phi, which means that if you now want to solve for I phi, that is going to be the square root of I0 squared minus IR squared. I0 is the same as I1 in this case. So I phi is all my markers decided to stop. Okay, there, that's better. I0 is given in the problem 2.5 amps. That's the input volt current here. Minus IR, we just calculated 0.45. So this gives I phi as 2.46 amps. Now it takes a lot more power or current to magnetize the core than it is dissipated in Joule losses, which is good. Now, based on this I phi, we can calculate the reactance X0. We can calculate L0 later if we want through the frequency. But let's calculate the entire reactance at this point. What is X0? Is V divided by I phi. That's the impedance of that particular inductor, 220 divided by that. And this is 89.4 ohms. And here we have the resistance of the core and the reactance of the core that it takes to magnetize it in a no load scenario. Remember now that we calculated this from the secondary winding. We now need to convert this to the primary winding. So as seen from the primary winding, what is the X0 equivalent as seen from the primary winding? This was calculated in the secondary. And now we want to calculate the secondary impedance as seen by the primary. So let's start with R. What is the R equivalent in the primary? Is the R in the secondary 484 times what?
N2 over N1.
Is squared.
Squared, right.
Is squared. We are now transferring impedances. If you do N1 and 2, this is A, and this is what we would use to transfer voltages or currents. Right? But now we are transferring the impedance from one side to another. So A is squared.
Sir, I have a question.
Yeah.
Isn't this all in the primary winding anyways?
No, this it looks like the primary winding here, but the test says in the example that this voltage was applied in the secondary and we left the primary open. Right? So if you take the secondary winding and apply the voltage, we are now magnetizing the entire circuit from the secondary winding. So it is the same as applying in the primary. This equivalent circuit looks exactly the same, but you are working from the secondary winding.
Oh, okay.
in this example. Okay.
So would you say then that because in this one specific test, the secondary winding is the primary winding?
Yes, we can say that. Yeah.
Okay.
Yeah. Very, very good. Very clear way to put that. So if we now multiply this by A squared, which we defined to be 10 based on the rating of the transformer, the equivalent resistance as seen by the primary is 48.4 kilo ohms. What is the equivalent reactance? Is 94.4 times A squared, which is 10, square 100, and that is that 9,840 ohms. Okay. Any questions here?
Sorry, could you go over why, because I think I missed why R1 and L1 are ignored?
Yeah, sure. So we see that we are leaving the open, one side of the circuit open.
Oh, just because it's open. So
it's just because it's open. So there's no current going that way. So they can be neglected. If we add an impedance in the secondary, then the current would flow there, and all this would, most of it would have to be recalculated.
Right, and because of that, that's why we said I1 equals I0, because
exactly
on that side. Okay. Now everything makes sense. And we used V2 in our calculations. We used 220 instead of 2,200 because again we're treating the secondary winding in this case, in this test, as a primary winding.
As a primary winding, exactly. Yeah.
I have a quick question. Can you hear me?
Go ahead. Yep.
Okay. So in the secondary winding, which is technically our primary winding in this case, we have a 2.5 amp current. How come, maybe I'm just misunderstanding something, how come you can just move it over and treat it as I0? Like, how does it transfer over even though we have a turn ratio in between?
Well, the turn ratio is accounted for here. You see, it's not that we are just transferring from one side to another. We are multiplying that by the square of the turn ratio. And that was given, let me go back here.
I think the pictures are separate. That's the question.
Back
Sure.
a couple. Sorry, I'll wait. I guess.
Now, maybe I'm not understanding your question.
Well, it was back, I think, a couple steps. I should have said something and I didn't. Back a couple steps when you were doing the calculation, I believe, for. Yeah, I think the calculation for I phi squared equals I naught squared minus IR squared. You
Yep.
just subbed in 2.5 for I naught squared. So you just moved over that current.
No, I didn't move it over. This is happening in the secondary.
Okay.
All this part here, all this calculation is happening in the secondary winding.
Okay.
This is the only thing we transfer to the primary.
So that 2.5 amp current isn't happening in the primary. That's actually happening.
No, there is no current in the primary because the terminals are open.
Okay. Okay. Thank you.
Yep. All right. So that's that. The second test will now happen with the secondary winding, the secondary winding shorted. So the idea here is a bit different. We have now the primary working as the primary, taking in this case 150 volts, and we are creating a short circuit in the secondary winding. Because we're creating a short circuit here, current flows through the secondary, and the current input is much greater than that parallel current that would go down, so you can neglect the whole thing. And the question is exactly the same now, but we are going to calculate that from the secondary windings perspective. So see if you can do it. As I erase the light board, it will take a second. And see if you can find the solution to that part. Now, the idea is a bit different because we are creating a short circuit in the secondary, so there's a lot of current flowing from the primary to the secondary. And that's what allows us to neglect a parallel branch because the current flowing there is negligible compared to the current flowing from the source to the secondary. And you're again interested in the same equivalent portions of the circuit, but now as seen by the secondary. We're just doing it the other way around. Okay, so let's do this one now. Now the test is a bit different. We are applying 150 volts here. We see a current input of 4 amps, 4.55 amps. And this is dissipating 215 watts. So how do we solve this now? How do we do the same, but now from the secondary perspective?
Can we perhaps start with the power being dissipated, all of it through the resistor?
Exactly, we can do that. The power dissipated through the resistor. Which resistor though? The equivalent.
The equivalent.
The equivalent resistor, RE here.
Oh,
Right? And
okay.
the equivalent in impedance, LE or XE. Right? Let me go back to this portion here. So we are neglecting this, and you're taking the secondary impedance R2 and L2 and moving it to the primary. And this is the equivalent resistance and reactance in the primary. Okay, so we can start with the power. The power is I squared times R equivalent. What is R equivalent again? R equivalent is R1 plus R2 A squared. And this gives us, we have the power is 215 watts. We have I. Now we can calculate R. So R is simply P over I squared, 215 divided by input current 4.55 squared. That is 10.4 ohms. Okay. Now we can try to calculate, so this is relatively simple. We can try to calculate now the entire impedance of the system. What is the entire impedance? If this is RE and this is LE, so our impedance is Z equivalent. And this is R plus LJ. And you can easily calculate the equivalent impedance here because you know the input voltage and we know the input current in this entire secondary part here. So Z equivalent is V over I, which is 255 divided by 4.55, and this gives 32.97 ohms.
Sir, should that not be 215 over 4.2?
Sorry, yes, 215. Yeah, that's my mistake. 215. Okay. All right, so now we have Z and we have R. How do we find L or X?
Sorry, is it voltage over current or power over current?
Voltage. This is the impedance.
So should it be 150 volts?
Yes, you're right. I use the same values from the first test. This is all 150. Yeah, it's all. So what is the power?
The resistance one is correct because the power is 215.
Yeah, this is 215. Yeah, 150. You're correct.
Yeah.
Yeah, I just copied the wrong number, but this is V. Yeah, V over I. All right. So if we have R and have X, how do we find? We have Z. How do we find X? The magnitude of the impedance squared is R squared plus X squared, isn't it? So X squared or X is simply square root of Z squared minus R squared. Z is calculated here. And minus 10.4 squared, this gives 31.4 ohms. This is, as seen, the equivalent reactance seen in the primary. This is the equivalent in the resistance as seen by the primary. How do we send this to the secondary now?
Do you divide by A squared?
Divided this by A squared, exactly. X divided by A squared, which is this divided by 100. And R secondary is R divided by A squared, which is that divided by 100, 0.104 ohms. Okay. Any questions here? No? All right. If there are no questions, then let's do another exercise. using the time that we have now. I always talk too much. Last year, I demonstrated a Jacob's ladder in class, because we are in person. This year, because I'm not planning on burning down my basement, I'm going to skip that. But maybe I'll make a video and post that later. If there are no questions here, should we move on? Yeah?
Yes, sir.
Okay. All right, so let's try exercise 7. For the circuit shown, consider the transformer to be ideal with a turn ratio of 1 to 100, so A equals to 1 over 100. Calculate the actual load voltage V2 and the supply current I1. It's a simple question. What is the load voltage? The load is the 30 kilo ohm resistance. And what is the voltage right there? Let me erase light board. I'll give you some minutes to think about how to solve this question. I mean, by looking at this diagram, we can maybe attempt to solve the current right away. Is the input current 110 amps? Is this correct? Is the input current 10 amps? Or 20 volts divided by 2? Yes or no?
No,
No. Why is that not the case?
because you have to include the 10K on the other side into the first.
Exactly. Exactly. So the reason I'm asking this is that I see this mistake very often on midterms. The students go straight for the easiest answer, 10, 20 divided by 2, 10. But then what happened to the impedance in the secondary? The impedance in the secondary has an effect on the primary, as we saw. So that must be taken into account. So the total impedance as seen by the primary is not only 2J, it's 2J plus the effect of the entire secondary branch. You need to account for that. Okay, so let's do this one then. We can start by creating an equivalent circuit. How would our equivalent circuit look like? It would look like the input here, which is 20 volts. Then you have a reactance. We have an equivalent load, and that's it. We have a turn ratio of N1 divided by N2, that is 1 over 100. We now can have a current here, I, and let's call this X equivalent and R equivalent. What is X equivalent? It's 2J plus 10,000 J times A squared. A squared. Right, is the impedance transfer again. All right, so 10,000 times A, the A is 1 over 10,000, so this is 1J. X equivalent is 3J ohms. Okay. What else? What is RE? R equivalent is what? The primary
30K.
doesn't have 30K times A squared. Right? The primary doesn't have any resistance itself, so it's simply the load referred to the primary, so 30,000 times A squared. A squared is, A is 1 over 100. This is 1 over 1,000, 10,000. It's 3. Okay, so 3 ohms and 3J. Now we can calculate the current. What is the current there? The current will be V divided by the magnitude of the impedance. What is the impedance? 3 plus 3J. 3 plus 3j, which is 20 divided by the magnitude of the impedance, 3 squared plus 3 squared. This is 4.72 amps. Not 10 amps, as one would guess in the beginning. Okay, is this clear? This must be very clear, 100% clear.
Mhm.
Yeah, no, perhaps. Now, all we did here was to transfer the impedance from the secondary to the primary. We came up with 3J and 3, and now it's back to electric circuits, nothing new. The current flowing there is the magnitude of the voltage divided by the magnitude of the impedance. The impedance is 3 plus 3J. It's a serial circuit. What is the voltage across the load now? What is the voltage across the 30 kilo ohm resistor? Well, let's start with the voltage here. What is the voltage across this 3? Let's call this V1. What is the voltage across this 3? Sorry, VL. Let's call this VL.
Is the current times RE?
Exactly. So VL is I times RE. I is 4.72 divided by times 3. This is 14.515 volts. So this is the voltage here, the voltage in the equivalent circuit side. How do we move this voltage now to the actual load here?
A squared?
A squared or A?
Just A.
Just A,
Oh,
just A, right? Just A. Very important. Again, a common mistake that I see in midterms. Now we are dealing with voltage. All the transfer that we did before was for impedance. Impedance is squared, right? Voltage and current is just A. It's just A. So the voltage now on the secondary will be the voltage L times 1 over A.
Oh, yeah.
1 over A. And this is 15 times 100. This is 1415 volts. This is the voltage right here.
Question.
Yep.
Could we have calculated the current as transferred to the other side, like solve for I2 and then solve for V2 that way? By
Definitely.
doing
Yeah.
IR. Okay.
Yeah, we could have determined the current in the output. You should get the same. You determine the current in the secondary winding here through that, and then from there you get 30 times that current is the voltage. It should give you the same result.
One more question.
Yep.
Say we have what was I gonna say? Say the primary side had an additional resistance or an additional resistor, so an input resistance. So when you calculated R equivalents, you would have added 30K times A squared to that input resistance,
Yes.
right?
Yes.
Now, if you wanted to find the V2 at the output resistance, you would have to just multiply the R, what is this? R2 A squared times I initial times 1 over A, something.
Yeah, it's a very good question. Let me repeat the question because it's very important. So if we add another resistor here, then our R equivalent would be that resistor plus this resistor times A squared. Now, this approach would not work to find the load voltage. We would need to find the voltage only across the load here, put 2 resistors in parallel, right? 2 resistors in parallel, and only find the voltage across the one that represents the load in the primary and then transfer that to the secondary. Or we go with the other option you suggested earlier. We find the current in the secondary, and then from the current in the secondary, we find the voltage across the load. Or, once again, have another resistor here in series that represents now the primary or resistance, and then this is still your load, so it should still hold if you do the voltage across the load on the primary, and then only transfer that portion of the voltage to the secondary.
Okay, there's one more question in chat. They were asking if there is no load, would we still bring the 10J inductance to the other side?
No. If there is no load, the secondary offers no resistance, no impedance to the primary. If there was no load, then our voltage here would indeed be, current would indeed be 20 amps. If you remove this resistance, there's no current flowing here. There is no impedance offered by this branch in the primary. So the only thing we need to consider is the primary itself.
Sir?
Yeah?
Can you also just explain at the very end why you multiply by 1 over A and not A? I kind of just don't understand that. Like,
we are looking at the voltage in the secondary.
yeah.
So V1 over V2. So if you look at this equation here, V1 over V2 equals to A. Now, right? We are fine. We are now interested in V2. We have V1.
Oh, okay. I understand.
Just
Yeah.
reverse. Yeah. Again, guys, do not make this mistake in midterms, because after all these things, and we go in the midterm, and then you forget that impedances is A squared, voltages and currents are only A. Right? Don't make that mistake. It's a very silly mistake to make. It's easy to make because you tend to forget, but it just doesn't make sense. This is A squared, and that's A. And
Hi, sir. Can I ask a question?
Yeah, go ahead.
When you calculated current, how come you took the magnitude on the denominator?
Yeah. So, how else would you calculate the current? You need to find the magnitude of the impedance, or let's put it this way. You could have here the current given in a complex variable, 20 divided by this, and then you multiply the top and the bottom with the complex conjugate of that, and instead of a number, you get a vector that represents the current with its real and imaginary part, and then you take the magnitude. So you'll come here.
Okay. Yeah. So it's just because it's complex.
Yes, I'm doing it early on, so we don't need to bother about removing the imaginary part from the denominator and doing that a complex conjugate thing. Right? But it's complex. Yeah, that's essentially
Okay, thank
it.
you.
We have 3J. Yeah, that's a complex part. A single transformer has 500 turns in the primary winding. When connected to 120 volts, 60 hertz power supply, the no load current is 1.6 amps, and the no load power is 80 watts. Neglect the winding resistance and leakage reactance, and calculate the core loss current, IC, the magnetizing current, and the peak value of the core flux, phi. So the question is very specific in the sense that it says neglect the winding resistance and neglect the leakage reactance of the winding. So what is left there? Apparently we don't have any load connected to the output. The only thing that is left would be the magnetizing reactance and the core loss in the form of this resistance. So we are applying here 120 volts. And this is taking 1.6 amps. And is dissipating 80 watts. The first question is, what is the current that is being dissipated, this dissipating energy in the core, IR, and the other question is what is I phi?
Sorry, sir. Could you explain again why it's 2 resistors this time instead of 1 resistor and 1 inductor?
Now this is supposed to be an inductance. I
Oh,
try
sorry.
to do an inductance there. Let me do this like that to avoid confusion. Okay. All right, so we know that it's dissipating 80 watts, and these 80 watts are being dissipated here. There is no other way for that to be dissipated. So IR is simply, if you do the power equals to IV, right? IR is the power divided by V. IR is 80 divided by 120. And this is 0.67 amps. That's IR. Now we can calculate I phi. We know the relation between I0 going down, that is splits in these two. We know that they are 90 degrees out of phase. We can write that I0 is squared equals to IR squared plus I phi squared. I phi can now be calculated as the square root of I0 is squared, 1.6, minus IR is squared, which is 0.67. And this is 1.45 amps. That's the magnetizing current, and this is the current created to that is dissipated, whose power is dissipated in the form of Joule losses. Okay, nothing really new here. The next question is, what is the peak magnetic flux? The peak magnetic flux, let's call this phi max, in the core.
Professor, just confirming, where you have a 1.6 amps up there, is that another inductor over there?
No, there's nothing here. We neglected the winding resistance and the leakage flux, so there is nothing there. This is the only thing that is left.
Thank you.
Yeah. All right, now you're interested in the maximum flux. How do you find the maximum flux? We are given the number of turns in the primary winding was 500. We now need to establish a relation between the core flux, the input voltage, and the number of turns. We can start by making an assumption that our magnetic flux is a sinusoidal waveform, like that, has a given frequency, and it has a maximum value. We can say that the magnetic flux at any instant in time is the maximum magnetic flux times a sinusoidal waveform that has a frequency omega. What is the magnetic flux? What is now the relation between the magnetic flux and the input voltage? We know that the voltage is N d phi dt, as we saw early on. If we now replace phi here and take the derivative, that gives phi max times omega in radians per second times cosine of omega t, all times n. N comes from n d phi dt. So this is d phi dt. So now V, if you only look at the maximum, we can neglect the cosine of omega t. V equals to n phi max omega. Now this voltage here is a trick. Everything that we did with regards to transformer rating was with respect to a RMS voltage. So this is not the RMS voltage. This is the peak voltage. Because you're dealing with peak magnetic flux, we need to find the peak voltage in the transformer. But our ratings here, when you talk about AC and transformers, are all done in RMS, root mean squared value of the voltage. With that in mind, now what is the relation between V max and V in terms of RMS? There is a factor of square root of 2. V max is VRMS times the square root of 2. It's a little trick here, but this would be specified in a midterm question if that happens. All right, so we have this square root of 2 factor that converts RMS into Vmax. So now this is our Vmax here. We can now rewrite this expression as Vmax is V square root of 2 divided by omega times n, and this is equal to the maximum magnetic flux. This frequency is in radians per second, and we are given a frequency in hertz. We know that this operates at 60 hertz according to the problem. So we can now rewrite n in hertz, omega in hertz. That is the frequency f. What is the relation here? Is 2 pi times, sorry, that's the other way around. It's omega equals to 2 pi f. Frequency in hertz, frequency in radians per second. Now our phi max can be finally calculated as V max, V 120 times square root of 2 is V max. So 120 times the square root of 2 divided by omega 2 pi f, 2 pi times 60, and times the number of turns, 500. And this gives 0.9 times 10 to the power of -3 Weber. And that is now the peak magnetic flux in the core of the transformer. And that's the last example. I will post the solutions to the other one. Are there any questions there?
Yes. Professor, why did we ignore the cosine component?
Because you're only interested in the maximum value. So the maximum value of the magnetic flux. You can always have this times cosine of omega t. Right? You can still have this times cosine of omega t, but the maximum value happens when cosine of omega t is 1.
Okay.
Cosine of omega t is 1, which is this peak value here. But well, we could write this. We could write that this curve is 0.9 times 10 to the power of -3 cosine of 2 pi 60t. This works. This is this curve. What is the peak? The peak is the maximum value of this function, which occurs when this is 1. Okay.
Did we just solve for B or C? This was C, right? The magnetizing flux.
This is the peak value of the core flux. Well, the B was the magnetizing current, which was that.
Then what's A?
A is the core loss current, which is this one.
Oh, okay.
A, B, and this whole thing is C. Very well. I will stop here. Any questions? No? Okay. All right. So thank you, everybody. I'll see you again on Thursday.